Okay, good. Thank you for coming. And how much time we have? Usually we have tutorial for 45 minutes. I want to compensate as much as possible for yesterday's lecture. So how you bound it in time? 45 minutes we end, and then our next tutorial I do the second part of the lecture. Or we can go a little bit longer. You can go, okay? So let's just, because we have recording, so and some people are on symposium, this new some, so we'll do recording as much as possible. When we are all brain dead, we just stop, okay, and then next tutorial I'll compensate. Because this lecture was supposed to be the last classical lecture before we start quantum things, and so I wanted it somehow to wrap. Okay, good. So, what this lecture is about? It's somewhat an attempt to look in the opposite direction. Namely, we mostly were talking how we can get maximum information and get it with zero, asymptotically zero error. Okay, so we were interested in maximum, let's say, of information transfer. We call it capacity. How much information we can transfer to a given channel. Then we understood that if our rate, how many bits we spend per unit object, is less than capacity, then we can it asymptotically error-free. Now let's look from an opposite direction. This is like a 20th century view. And 21st century view is we have so much information. I mean, how we can get rid of maximum of it, keep as little as possible, and still reach our goals. And this is a subject of a quantitative approach, which is called rate distortion theory. It's a formal, again, I'm trying to teach you, like for natural scientists, some subject for which there are semester courses or 1 year courses in a big textbook with that name, right? I'll try to explain you the essence of it, so if at any moment you would need something similar, you would know what it's all about. So it tells me the following things. Imagine that you really can afford some distortion. So namely, we again are talking about standard setting. So we have B, which is our source outside world. For me, it always, I imagine that, let's say, I'm trying to design self-driving car. So B is a world outside, okay? And it sends me a signal which I record, and it's A, okay? So before, we were looking for mutual information between A and B, and we were asking what is the maximum of it. We took maximum of it over all possible of statistics of B, and says that's the best thing which this channel can achieve for particularly very good B, then we call it capacity. Now we'll be looking for minimum. Namely, what is the minimum that we can have, namely, how little we can encode in R. Let's say that we have R, the rate R, which means that there are the whole set of values of AI run from 1 to 2 in the power R. R is in bits, okay? So if you have like 3 bits, at every position of your bit could be 0 or 1, so you have 8 possible values. If you have 10 bits, it will be 2 in the power 10. So in this rate distortion theory, rate is 2 in the power rate is how many values of A you record. For example, your B could be something which is analogous signal, some electric current or any rational number, which potentially you need infinite information to record any rational or irrational number. Okay, but A is no, it's just a finite amount of information, and R is how much? Okay, of course we take logs, which means that 2 in the power R is a number of values, but we say apparently if whatever value of B I have, I need to choose one of these values, right? and it will not be exactly equal to the value of b. Okay? Even though I maybe receive this value of b, but I record one of these discrete values, so I would have some distortion d, which is of course a function of a, I, and bj. So there is for some value of bj, if I take this value of ai, there will be some distortion. Okay? And first time we've seen it in high school when we used the least square method. Right? So we were saying, okay, we'll quantify, here is my points, which I record, and there is my continuous line, and so I just sum square. But there, of course, could be different measures of distortion, but let's start from the simplest one. So first case is a distortion is a variance. Namely, we define that d of any values of a and b would be just a minus b squared average. Average means that there will be b signals coming with their own statistics, will be recording a's, and every time checking the difference, squaring and averaging. And we say we can afford having this distortion less or equal than some d. This is just a number. Okay? Which means that the meaning of this rate distortion theory is the following. You set distortion, what is the mean value of whatever function you choose, which determines how you distort b, how you deviate. So you can you pose a condition on that your distortion is less or equal than some number, and you ask what is the minimum r which can give you this. Okay? How to do it? Let's start from a simple case. You have one bit, and b, let's say Gaussian. So p of b is 1 over square root of 2 pi sigma exponent minus b squared over sigma squared, 2 sigma squared. It's zero mean, and variance is given, but for a you have one bit, namely 0, 1. Okay? What you can then record every time you get any b, you can record. What you can record about b? Yeah, you can only record sign. Yeah, you have an interval of b. For in this case, it's minus infinity plus infinity. Something or any interval, you can divide it into two parts and say one bit tells you right part or left part. That's what this bit is about. Okay. So in this case, you can say, okay, which value of a I need to take so that this would be at the minimum value, and you can compute it as, of course, the mean value of b modulus, because you know the sign. Okay. Now, what you want to really get is you want to get a function, namely this d, and you are interested in this r. So you want to get r as a function of d for minimum. Okay. Yes. So how to do it? You set a variance in this case, and then you ask what is actually the rate of transfer of information from B to A. Capacity is a maximum of the rate. But generally, for any conditional probability of having given B under a given A, there is a rate, which is
mutual information.
Of course, it's a mutual information. This mutual information is exactly this rate. Right? That's by definition the mutual information. So what you're now looking for? You're looking for a minimum of a mutual information under a given variance. But we know what is a mutual information between A and B. it's S of B, which is given by whatever statistics P. In this case, we know P of B, so we know S of B. It's S of B is given. It's just a Gaussian. It's a logarithm of sigma. Yeah, with all the pi's and e, but mutual information is not S of B. It's S of B minus what?
S of A under B.
Yes, it's a conditional. Namely, this was what before we started receiving A. After we receiving A, this remaining uncertainty. The difference between them is how much information passes through this channel or how much information are in A about B. So we're now looking for the maximum of it. This is given, which means that we're looking for maximum of this under a given variance of A minus B. What probability? We can do different things. For example, we are essentially asking what is this, to get this maximum of this. We can choose different probabilities. Probability of B under a given value of A. And what we set is a distortion. So this is A plus D over 2, this is A minus D over 2, right? So we now allow distortion around any value of A. We allow distortion variance, right? In this D interval. So now, one option, we can choose the probability of B under a given A is, for example, like this. Right? So it can be 0 outside of this interval and 1 of this interval inside. Will be uniform. Right? Will it have maximal entropy under given variance?
Maximal entropy under given variance is Gaussian.
Exactly. So second option would be to take P of B of A as a function of B, it's a probability of B, at any given A as a Gaussian having variance D. And we know, and in 5 minutes, when we derive the general formula for any D, we will see that, of course, if you're really looking what is the probability distribution with a maximal entropy, we look for maximum of this because we look for minimum of this, right? It will be Gaussian. Okay? So now, if you say that my rate is a minimum over all P of B of A's of this quantity, and this would be now Gaussian, this, which would be, I just want all 1/2 to be, and this would be 1/2 log sigma squared, and this would be minus 1/2 log D, and I omit all 2 pi e because they are the same in both cases, so they just cancel out. So what I would get R as a function of D, which is called rate distortion function. How my rate depends on distortion, and it would be 1/2 log sigma squared over D. That's, in a sense, the main formula of rate distortion theory. It's a big theory, and this is, of course, something which appears at the beginning, but it's essentially the most basic formula. There is something surprising about it. Well, first of all, when D goes to 0, what happens to the rate? It goes to infinity. You want it to be with a less and less and less distortion, you need to record more and more and more bits. And it tells you how it goes to infinity. It goes logarithmically. Okay? So as long as your window shrinks, you need to record more and more bits. Okay? Now, let's increase. Let's say, okay, but I can afford the d larger and larger and larger. What happens to this function? So first of all, let's just plot it, right? So r and a function of d, when d goes to 0, it increases, okay? When d equal to sigma squared, what happens to it?
It's equal 0.
It gets 0, absolute minimum. We repeated ad nauseum that mutual information is always positive, right? Couldn't be negative. Okay, so what does it mean? Well, you definitely cannot continue it, right? Think about it. So what we say, we have Gaussian statistics of signals. We choose it for simplicity with 0 mean. You can add mean. That would just 0 bits, right? Mean is a mean. You know it. And then you say, okay, I can afford distortion, which is larger than the variance of my signal. This formula tells you, you don't need any bits for it. Absolute minimum, 0. And this has a perfect engineering sense. Right? If from your viewpoint, which is the resolution of your theory or your device or whatever, the variance is small, or d is larger than variance, that's not something that you need to record. Right? It's a non-fluctuating quantity. Your fluctuation of d is too small. You don't distinguish it. If there is a mean value, so there is a mean value. You know, okay, this is a mean value, and I don't care about fluctuations around it. My distortion is larger. Okay, that's a simple message. That this rate distortion function is something which can just hit 0, and 0 is an absolute minimum. No information. Questions?
Do we get from this the way in which we can maximize the rates, like the actual function of A?
For this, we did a very, very simple exercise. We've chosen Gaussian statistics of B, and our distortion function is variance. Namely, it's a least squares method. We're looking for, okay? So now we'll do a general case, but for this particular case, we know in advance that this entropy is also logarithm of variance because Gaussian distribution gives the maximum.
Yeah, but we know that the probability of B given A is Gaussian. It's not exactly given as A is a function of B. Like it's not exactly that we say.
We don't need A as a function of B. We actually are asking for conditional. We were choosing conditional probability of B under given A, which means that we obtain value of A. Now, I mean, you engineer it, so you say, okay, now I need to tell my system what possible values of B it can assume, given that value of A. And then you ask how many values of A I need to record, right? So that with a given accuracy, I can afford obtaining this signal. Question? Just meditate a bit about it. Now let's solve the general problem. And of course, the general problem means that we now assume that this function d is not necessarily quadratic. Namely, that it's not necessarily variance. Namely, that there is some function d, but we again will look for a minimum of mutual information. So, let's just. So I will be looking. So I will be looking for the minimum of A under a given mean value of D, but my function D of A and B will be arbitrary function. Okay? So I'm looking for this, and this is now not this, but just a given function. Can you immediately tell me what I should choose for this probability of B under a given A, or for the probability of A under a given B under a given B?
Again, what's the whole function?
Anything.
What?
Anything.
Anything.
Just a given function. For example, for Hamming distance, distortion is something which is unity when you're exactly at a given bit, or zero when you are not in this bit. Or it could be a minus b in the power 4. There are many, many different functions which you can choose, but now we're looking for a general formula which tells me how to choose, let's say, conditional probability which would minimize this under a given value. Okay? So, yeah.
Exponent of the function.
Of course, you already know that whatever is given is in the exponent. Okay? So let's see again in the game how it appears, but it always appears in the same form. So let's say that what I need to do, let me first write mutual information. This is the probability of A and B, so I'll write it in this form of A and B, and the probability of B, and B will be J, and A will be I, and I will sum over all values of I and J, and this would be a logarithm of the same P of AI under Bj over P of BAI. This is my mutual information, exactly written. I hope you recognize it, right? This is just a joint probability written by the chain rule, and this is this ratio. And now I also need to add to it with unknown Lagrangian coefficient beta, and of course they always, I mean, even AI people usually call it beta because it's came from one of the temperature in physics. And what stands here is d over AI and bj. So when I sum this with this would be exactly d, my mean value of my distortion, right? So by Lagrange method, I need to find this conditional probability, which now realizes extremum of this function. You remember, right? Which means that I need to differentiate with respect to p, and I need to also differentiate with respect to beta. With respect to beta would give me, well, technically what must be written here is this one, right? So I add the condition that the mean value of this function d is equal to this number d. Okay? Now, as you now say, that what I want to take this I plus beta d differentiated with respect to probability of A, B, or BA, depending which you are looking for, and requires it at 0. That's a condition which would give me an extremum. And when you differentiate this, you find out that you get this plus this equal to 0. And that's precisely how you find out that the probability of AI under given Bj is the probability of AI, which is this one, times exponent minus beta d of AI and Bj, and of course divided by some partition function, which is now is only, because it's a probability of I, it cannot depend on these values, right? It only depends on this. This is condition probability, conditioned on B, so that depends on Bj, and of course the value of beta, which you find by, which is expressed through this number d. Okay, that's a standard Lagrangian method, and we're doing it almost at every lecture, right? And so if you did not do it yourself on the page like 5 times, do it. Right? This is really. So now, of course, z is a partition function, which is just a normalization factor, which is sum over I of p of ai exponent minus b d ai bj. So if you divide by this function, then this will be normalized. When you sum over all possible AIs, it would give you 0 when you choose z in this form. It's just a usual normalization function. I intentionally wrote it for this conditional probability to stress that it expresses p of ai conditional on b through a no unknown function p of ai, right? Because what I know is p of b, right, which comes outside here. So there is p of b coming. I need to choose my conditional encoding. How I encode ai for every given b, right? That's what this encoding. And now, but it's expressed through this. So now I need to relate p of ai and p of and p of b. How I relate it?
Chain rule?
Huh?
Chain rule?
Chain rule. There's only one way to relate one probability of one set A and another B only through conditional probabilities between A and B, which is the same probability which we are looking for, right? So now I can write the chain rule, namely that I need to sum over all j and multiply by a probability of AI under a given bj, right? That's my chain rule, right? Probability of every AI is a probability of bj times conditional probability and sum over all j's, right? Now you see that this is a system of linear equations. It's not an answer, right? It's expressed this through this, and this expressed this through this. Okay? But, well, come on, this is a system of linear equations, and computers do it very, very fast. This is really not something that you need kind of AI or deep learning or whatever. But this is a solution of the problem of rate distortion, which gives you, when you solve this system, it gives you this probability. It always have exponential as an exponent of a distortion rate. After you find this, you compute mutual information, which is this guy. And this is your rate. Okay? And the rate is always monotonic function of d and a convex function of d. And you can spend semester really proving this always beautiful statement. But this is the essence. Is that clear? Okay. So you set whatever function of a and b. It could be very, very different. Okay. And you say, I'm looking for minimum encoding with mean value of this function given. Then this function will get the exponent. Okay? You don't need to compute anything. You just know it will be an exponent. What you need to compute is a factor in front of this exponent. Okay? That's the name of the game. Is it clear? Is it okay? You want to meditate a little bit, think about it. This is a system. It's a system, right? So this is for every bj, right? And this is for every. These are big vectors, and this is a system of linear equation. And you do these matrices, you invert them, etc. You solve it. Okay? But it's not really the problem of self-driving car. Self-driving car does the next step. And that's what, where all this continues, is that this is your outside world, namely other cars beyond your car. This is your camera. But there is a processor which really makes decision, right? Turns right, left, stops, accelerates. And this means that somehow a signal from this A goes to some C. This C is used the notation C because it's encoded, code, in this code book. And what you really want, this is your device, it's given, okay, so it has many pixels. And usually, I mean, our eye gets 10 to 5 bits per second. Normal in your smartphone camera gets the same amount of bits per second. It's really huge, right? You don't need it to process. We know that neurons, the first generation neurons of our eye, send like between 20 and 50 bits per second to the brain. Which means that you need to do a huge compression. All the science is about compression. How little information you really need, but now not to encode in A. A is still a lot, but encode in C. Okay? So you'll be looking at some conditional probability of putting, you know, as it should. Okay? So you'll be looking for conditional probability of encoding, what I call it, CJ, under a given condition AI. But on the other hand, there is a conditional probability between B's and A's. Okay? So what is the optimal scheme in which you want to proceed? You again need to minimize, apparently you would be wanting to minimize mutual information between A and C. Namely, encode as little as possible about A, first of all, because most of the visual information is totally redundant. In any, I mean, in your eye or in any camera, next pixel is practically the same as its neighbor, right? So you want to compress all this to few bits. But what are those few bits? So you need to minimize this, keeping something else, or maximizing something else. What is it else?
Contrast.
I'm not asking about contrast. Contrast is a physical signal. I'm asking about entropies, mutual informations. Okay? So, in a sense, this is what I'm now calling is a kind of a next step after rate distortion theory, and it's now very famous. It's called information bottleneck method, invented by here in Israel. Well, there were several authors, but Tishby in Jerusalem one. So, what you want, kind of meaningfully, you want you see, namely, what comes to your processor, your decision maker, to know, to get as little as possible about A, but it still need to know something about what?
B.
About B. So you're really interested not in all this redundant information on your A, on your camera, but you want to know something relevant about B, which is an outside world. Okay? So, and what quantity would characterize it?
Information in C.
Who says it? Mutual information between?
B and C.
Yes. Mutual information between C and B. Okay? So, despite extreme simplicity of this idea, it's really a relatively recent invention and also technically surprisingly non-trivial. And let me explain and show why actually it is non-trivial. Okay? So, the idea of Tishby and Coulthard was that you look at this quantity and you look for the minimum of it, but you add with unknown Lagrange multiplier a factor which is I, C, and B. Okay? Namely, you're looking for minimum of this whole functional, and as always, it's all free energy type approaches. I hope you recognize. Every time you have two-term functional, it's a free energy. It's always E minus Ts F. So you're looking for the minimum of it, and you can reach it as a minimum of E or maximum of S. Okay? So you're looking for minimum of this. You can encode as little as possible, or you can keep as much as possible about B. But beta tells you what is a balance. Beta essentially tells you how much you care about B. When beta goes to 0, you don't much care about B. Crash, no crash, okay. You just want as little information as possible. When beta is getting large, then of course all your optimization is that you really need to keep as much as possible about B. Okay? Now is that the whole idea is clear, I hope. It's really, the idea is very simple, right? So you want to keep as little as possible about A, but as much as possible about B. That's, or why they call it information bottleneck, it's, I still remember, Tishby, he died a few years ago. He always like saying that you need to squeeze this huge information through this very narrow bottleneck and still keep a little bit about B so that there will be no crash. Okay? Let's write conditional probability and see how the formula will work out. Okay? Questions here? You with me? The moment you start get tired, I mean, we stop and continue next. So, what I now write this down, I will say that this is again the sum over all ij, and this would be, again, I write by chain rule, I write a joint probability, namely that this is C and A, which is P of A. Again, we all read the chain rule from the right. The probability of A times probability of C under A. And this guy is just a logarithm of P of C of A divided by P of C, and then minus beta. And what stands here is now the sum, but it will be J and K. J's are about C, right? So this would be C and B, so it will be CJ, BK, okay? And so it will be P of B, K, CJ, P of CJ, and the same logarithm, but now the logarithm of P and B, K and C, J over P of B, K. Good. How to differentiate it with respect to what? We have now two things. One is this, and another is this, right? And if I differentiate it with respect to P of C, of course, I will differentiate this, but this is something which contains B. So now what I need to ask, are they related? Are these two probabilities? You see, these probabilities are probability, again, this is BK AI. Okay? So I am relating probability, I'm taking a given AI, it's in the middle. That through it, through A, they are related, right? And now I want to relate this conditional probability to this. What would be the formula? Let's say I would relate this one. how I express this through this.
PBK given CJ times PCJ given AI.
Wait, P, so first of all, what must be there? AI would stay, right?
Yes.
Yeah. AI, they have the same, so,
Sum over J.
huh?
You need to sum over J.
Because CJ, no, I did wrong. I don't need this one, sorry. This is the wrong formula. I feel that because I need C and B, mutual information, right? And what is written here, so I really need this one, right? Because I need mutual information. Sorry, this was a misprint. So now it's clear that the sum must be over I, right? Because this would be, so this would be, I can write as usual, if I multiply it by Cj, right? This is the joint probability of Bk and Cj, right? But I can write it, of course, by summing over I, namely by all. So I can come into this pair one way from C to B, but I also can come through A, and this would be as following. So I start. Where am I start? Okay, I start from P again. I'm writing it from right to left. So I start from P of A, then I multiply for the probability of Bk under given AI and the probability of Cj under given AI. Okay? And that way, again, I get linear relation between conditional probability of this one, which I'm looking for, and that one, which I'm looking for, namely that now, when I can take this expression, for example, I would differentiate it with respect to P of C, A, right? Namely, I'm looking for this distribution. So when I differentiate it with respect to P of C, I will differentiate this, I will differentiate this, and when I would be differentiating this, I will use this formula. So I will take this formula and differentiate it, namely, I will differentiate and I would get this one. Okay? So relation here is linear, so the derivative is linear. But this formula is not linear with respect to P of C of A. Right? You see? So now when you differentiate, for example, with respect to this, so you would get this logarithm, but when you differentiate this, you would get this combination. Okay? With its own logarithm, and now you would need to put this formula into this logarithm as well. It's a nonlinear relation. So now what you get, the question?
Yes. For this formula, like for this sum to be true, don't you need to assume that given A, then B and C are independent? For like to break apart.
Well, they're all dependent. I mean, if you look here, there is a conditional probability. Of course, they are dependent. There is mutual information between C and A, which we explicitly look minimum. And of course, there's mutual information between A and B, but we don't look for it. Right? Instead, we are looking for mutual information between C and B. So we expressed it through the chain rule, saying that you want to know what is the probability of a given pair B and C. Choose every value of A, you sum over all i's. For every value of A, take the probability of B, K, under this value, times the probability of C, J, under this value. Okay? Because the moment you fix this value, they are already dependent only on this value, not on each other.
Okay.
Okay? So this is a chain rule which gives you. Again, it's every step is conceptually trivial, but you know, when I was learning this stuff, and people just gave a colloquium at physics, and I was really impressed by this. maybe 8 to 10 years ago, I was just set and took 3 values of it. I usually don't trust formulas. I use like I take 3 values of A, 3 values, 2 values of C, etc. And then I'll try to just do all the arithmetics here. And then you see how damn nonlinear it is here. But here it's still a linear relation. But the focus is that when you substitute, again, it's a linear system, right? It's a vector in terms of B, so you're looking for this. So this formula essentially need to be written as follows. And because you're looking, it's 1 over P of Cj times this sum over I. Okay? And in terms of relation of these things, I mean, it's linear with respect to B, but this P of C comes as a factor. And the whole, this system is a system on 2 vectors, right? So for every A, these are 2 vectors. And these 2 vectors are in a system which is nonlinear. It's not a linear system, it's not something which you solve just by inverting determinants. And here, that's where deep learning works. Generally, deep learning algorithms, they solve such type of system, which they do iteratively. Namely, they say, okay, let's fix this and look for the extremum with respect to this. After that, you do it, and this apparently you fixed this, and it's something not yet optimal. So now, what you find is you fix this, and you now do iteration you solve with respect to z, and then you. It's called deep learning. Namely, there are many steps or layers of this iterative procedure. This it's now done much smarter than what I'm explaining to you, but that's the idea. Question.
I was going to ask about the relation between this formalism and autoencoders. This is like
And what?
autoencoders.
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 I don't know. This terminology is unknown to me. Yeah. Again, I mean, this is now such a huge field that what I'm trying to tell you is just the basic ideas which are there. And technically, there are many things already working deep under the hood, so you don't even look how they are inside. But generally, this is a basic idea which tells you how the same powerful notion, mutual information, works over and over and over, and it can work always. It can work that you're looking for its maximum, and that would be capacity, or you're looking for its minimum, and that would be rate distortion, or like in this information bottleneck, you're looking both for the minimum of one mutual information and maximum of another mutual information. And every time you have 2 competing things, free energy balance. Of course, this is free energy. And they call it free energy. And then what happens really like in physics, when you change temperature, what happens in physics are phase transitions, right? So if your temperature is very high, then you reach your equilibrium state by maximizing entropy, namely you have a gas with a maximal disorder. When you lower temperature at some point, this starts playing a role and you create liquid. So what these people discover, that when they change temperature, their algorithm also undergo phase transitions. Namely, at some point, they would kind of abruptly switch from maximizing this to minimizing this. Well, not abruptly, I mean, they still both play a role, but very different. And also convergency change, etc. But let's, now I want to finish this, at least to write a formula, which is, so let's differentiate, so when you do differentiate this with respect to this, right? So what you essentially get, schematically, I just want you to see how it works schematically. You say that you would have a P, you differentiate with respect to this, so you would have something like P of A, you have a logarithm, and this logarithm will be of P of C of A, what you're looking for, right? And this would be equal to beta from here, right? And it will be P of C and derivative of this with respect to it. So let me write it kind of schematically. dp b of b c over dp of c a, and then you take this formula and you differentiate it with respect to this, and so what you get eventually is a formula which again is not a formula, it's still an equation because it contains your unknown things, but I just want to show you how familiar it looks schematically because it's always the same. It's an exponent. The question is what is exponent of what? So P of Cj under AI, what is the encoding, right? How you need to encode every value of AI? It's a P of C J divided by some Z, which is, I don't want to now write it again, is a function of AI in beta. And what stands here, it's minus beta sum over all k, and this is P of B k A I, which comes of this formula. So you differentiate with respect to this comes over here. This is something which is your camera. This is how your camera works, right? It's not about your encoding. You ask how I need to encode. What is the code? The word C must be for a given A. And this is a conditional probability of relation between outside optical image and your camera signal, right? But what stands here is a log of and this would be the last formula. You're still alive. What is this? Now I want you to, when I was first year students, they told me that in theoretical physics there are two methods: multiple rewriting and staring. Okay, so I did a lot of rewriting. So now I want you to do staring. You just look at this and you don't do it. You just look at it. So what is this? Huh? Yes, it's relative. It has a structure P log P cubed. Right? See? How the same thing. So now what is this relative entropy? Let me write it explicitly. It's a D. Unfortunately, and it's called Landau rule. Whatever you have one letter determining two quantities, they always will meet in the same formula or on the same page. So this D is not D what is one in the distortion theory. It's a relative entropy. That's why I would put a bar in between. Okay, so it's a D between probability of B under given A, and I put two, like separated, okay? And this is the probability of B under given C. So essentially it tells you that your probability, you still, need to kind of resolve it, right? But conceptually, it's again very, very transparent. Beta is here as a factor. It's a very, very transparent formula which tells you that the probability of encoding that you are looking for is something which is exponential. And here is a relative entropy, which is again non-negative. It's really important, right? This is something which this quantity is always, whatever will be coefficient there, and it's between what is the probability under a given A, which is your quality of your camera, and the probability of B under a given C, which is the quality of your encoding. Okay? So even though it's technically a quite complicated system of nonlinear equations, And of course, computers, made of iron, and they can now run it very fast, etc. It's not technically a simple thing, but conceptually, it's a very transparent thing. Okay? So your rate is your mutual information, and your when you simply looking for the minimal rate of transfer or the minimal rate of recording, it's given by rate distortion theory, namely your probability is exponent of your distortion function. If you have a two-step process, namely you record something and then you will encode it. Encode it as little as possible, keeping as much as possible, then your probability is the relative entropy. And then again you see physical intuition is very helpful. When temperature is very large, beta is very small. Which means this is not very relevant. When beta is very small, whatever maximum minimum of this function is just a little bit changing your probability. Okay? But when you start cooling it, and they call it annealing in statistical physics, and again, what mean in this case means that your deep learning system changes from iteration to iteration, changes your beta, and then this is starting to be more and more important. It's a hugely multidimensional space in which you're looking at this, right? And then you kind of slowly come to the extremum, to right optimum in this respect. Okay? But again, it's always this two-term function. Okay? So that's what I wanted to tell you. And money will be next week, okay? Because I actually wanted to make a second hour about money and stock market and all this. So next tutorial will be money, but lecture will be quantum next month. Questions? Okay, good. You must be already very tired.
Again, this is the relative entropy for a specific A and C, right?
Huh?
Like, this is the relative entropy like for specific A, I, and C.
Yeah, of course. I mean, when you look here,
Yeah.
it's all, but then again, here you sum over 2. But AI is fixed because you're looking for probability at a given AI. Okay, right?
And again, in the capacity distortion, we're looking for, it's not the maximal capacity, it's the
Capacity is the maximum of mutual information.
but under the given distortion, we're asking what's the minimal capacity.
We're looking for a minimum of mutual information.
Okay.
Okay? Because in the capacity, we want to get as much as possible about the source. In the distortion theory, we get as little as possible about source, but still not exceeding this distortion. Okay. It's totally opposite viewpoint.
Oh, it's lossy compression. We want the capacity to be, okay.
Capacity does not appear in this, because capacity is always about maximum, by definition. Here, we're looking for minimum of mutual information. And this is called rate for a given distortion.
Okay.
Mutual information is always rate. But now we're looking for minimum, and then it's called rate distortion.
Okay, got it.